Okay, so anyway, and then is there life elsewhere in the universe, which is a pretty good question. So how do millimeter waves address these? Well, it addresses it primarily because molecular clouds are the places where stars form. And so if you want to learn about star formation, which gets you into the whole business, at least of how the stars form and evolve, and how do planets form and evolve, because that's part of star formation. And it's also important to questions of how do galaxies form and evolve, because the evolution of a galaxy depends upon generation after generations of stars forming and going through their cycles and returning material back into the interstellar medium from which new generations of stars are formed. So this whole question of star formation is really central to a lot of these key questions. It turns out by a happy coincidence that millimeter wave emissions from molecular clouds and galaxies, and in particular very distant galaxies, are a great way to pick out galaxies at very great distances. And so we can study these clouds in very distant galaxies. And of course, in astronomy, as we look farther and farther away, we look farther and farther back in time, which means that if we can see far enough away, then we're looking very far back, maybe 90% of the age of the universe, seeing things as they were when they first formed, and then we can look at them at different distances and see how they have evolved, how galaxies have evolved with time. And then finally, by looking at the millimeter wave emission from protoplanetary disks, we can study the chemistry and the physics of these disks and begin to learn something about their origin and evolution. There's another interesting trick, and that has to do with looking at the cosmic microwave background. As you may or may not know, the cosmic microwave background is this light that was given off very early in the universe. It's basically, you're looking back so far in time that you're seeing the universe as it was when it was still hot and opaque. Basically, the conditions are like the conditions you now see in just localized regions like the Orion Nebula, where gas is all ionized. You're looking back in time, and we see structures back in time, and so the LMT, looking at the fluctuations in the background, can help to determine some of the fundamental properties of the universe. That's how a lot of the current knowledge of the fundamental constants of the universe has come about from looking at this radiation. And then there's also a trick in terms of looking at the cosmic microwave background. It's a great way to find very distant clusters of galaxies, which can then be used. The numbers of these galaxies can then be used to constrain the models of dark matter and dark energy. Just to show you that astronomers are serious about all of this, there was a survey done of the most cited papers over this period of years, and what areas were people talking about. And number one on the list was the cosmic microwave background and the fluctuations, which is essentially COBE was a millimeter wave, a WMAP or millimeter wave instruments on those satellites. And of course, this is the work that just won the Nobel Prize in Physics this year. So I guess other people, astronomers, thought it was interesting. And then there was another discovery down here, number 6 on the list, which was the discovery of a population of very young galaxies, or distant, early in the history of the universe, that was discovered at millimeter wavelengths. And it turns out that that's the population of galaxies that the LMT is going to do a great job of serving. These are some of the other instruments that are going to address some aspects of millimeter wave astronomy. I'll just point out, just wanted to give them, I'm not going to give equal time, but I just wanted to point out the Atacama Large Millimeter Array, or ALMA, is it's the biggest project underway in astronomy in the U.S. at the moment. It's a $1 billion millimeter wave telescope that's made out of 64 individual 12-meter antennas wired together as one giant antenna. It's a collaboration between Europe, North America, and also Japan, although Japan has a kind of a unique way of joining collaboration. So, but in any case, so it's a huge worldwide effort, $1 billion here. There's also a smaller such array, which is run by a university consortium, including Caltech and California, Berkeley, and Illinois, and University of Illinois, University of Maryland, and University Chicago that is out in California. It's basically a much smaller operation, but nevertheless it has a certain amount of sensitivity, and it's actually in operation right now. And then there's a large telescope built in West Virginia. It's a 100-meter telescope. It's built primarily for longer wavelengths, but they think it might be able to use it at 3 millimeters wavelength eventually, so I have to include it on this list, or else when other people from other projects see the list, they'll say, oh, we forgot to bring that telescope. But anyway, if you compare us to them, we would be the world's most sensitive single antenna. ALMA is the most sensitive, will be the most sensitive millimeter wave antenna or telescope when it's actually finished in like 2013 or something. We exceed the sensitivity of our nearest university-based competitor by a very significant margin, as you'll see in a slide here. And for some kinds of experiments, we're competitive with ALMA. There are certain classes of experiments that we can do as well as they can do. Just to prove that, here are some numbers. Everything that's in red, I have to confess that we selected our metrics rather carefully, but everything that's in red here is something where the LMT can do better than ALMA and those other examples. And so, you know, we will be the best single dish in the world, so-called, and we can do some kinds of experiments better than anybody. So if you think about us in astronomy, what you hope in your observatory is that you're going to contribute to a lot of different areas in astrophysics. And so we're going to be able to do things in the solar system, molecular clouds, and the galaxy. And we're going to be able to study other galaxies. But there's one area where we can make a really exceptional contribution, and that's the area of looking at very distant galaxies and seeing them as they were at their earliest stages. And the LMT is going to be able to, is really going to make its reputation by studying the formation and evolution of galaxies. And I'm going to just try to give you a sense of how that all works. So here is the discovery. That you remember, number 6 on the list was the discovery of a population of distant star-forming galaxies. And this is the discovery picture. This is the Hubble Deep Field over here, and what a bunch of guys did was they went and they used the James Clark Maxwell telescope in Hawaii and made a sub-millimeter picture of the same thing. They spent a month, day after day after day, in the best observing conditions that had ever been observed, according to David Hughes, the author of this. And they found 5 objects in here, and don't ask me to point out which are the 5 after those 2. Okay? So they found this set of objects which hadn't been anticipated particularly, and based upon that and follow-up work, we now understand that there are a lot of objects. And what you're seeing here is basically something like a near phenomenon, which are called ULIRGs, another terrible acronym for ultra-luminous infrared galaxies. These are objects that are basically have very high rates of star formation occurring in them, that heats the gas and causes them, and heats the dust in the galaxy and causes it to be a powerful emitter of infrared radiation. If you look at the spectrum of this thing, you find that there's a very big peak out here at about a wavelength of 100 microns, corresponding to the peak of the black body spectrum for gas at, say, 30 degrees or something like that temperature, which is more or less what you see. Now, one of the interesting features of this spectrum, you notice that you might say, okay, if I want to go find these things, the wavelength I should pick is right here at about 100 microns. And you might say, well, you know, why are you guys building a millimeter telescope? Because that's way over here. But the answer is that as we look farther and farther away, we have the redshift, right? So what happens to the light from more and more distant galaxies? It gets shifted to longer and longer wavelengths. So in fact, as we look farther and farther away, this big peak gets shifted over into our wavelength band. And what that means is that we can sit here and we can see everything out throughout the entire history of the universe, because basically this big bright peak is being shifted, so the galaxies to us are looking brighter and brighter